Far beyond the Milky Way, a giant galaxy called NGC 4889 drifts in the dark heart of the Coma Cluster, wrapped around one of the most massive black holes ever found. Tonight's documentary gently unwraps that cosmic center layer by layer into a calm, sleep-friendly journey through clusters, galaxies, and a silent dark core that holds them together. If this kind of science helps you relax, please like the video and subscribe so more quiet stories from the universe can find you. NGC 4889 sits near the crowded center of the Coma Cluster, a smooth oval of light more than 300 million light-years away. In this dense gathering of galaxies, its presence matters, because it helps reveal how gravity sculpts structures on the largest scales the universe allows. By the end of this journey, the dark heart buried in NGC 4889 will feel familiar. Around that hidden core, a hazy sea of old stars glows against deep intergalactic black, shining like a soft lantern in a silent hall. Its quiet influence on the galaxy and cluster will also feel understandable. The core idea of this opening stage is simple. A single galaxy in a cluster can act as a guide to the cluster's entire story. NGC 4889 appears peaceful at first glance, with no bright spiral arms, no obvious dust lanes, and no dramatic jets cutting across the sky. Its light forms a broad rounded shape, the classic form of a giant elliptical galaxy, built from many past mergers and encounters. In plain terms, it's a vast smooth population of stars bound together by gravity that reaches far beyond what the eye can see. The Coma Cluster itself stretches much wider, a deep well of matter in which hundreds of galaxies drift and orbit in long, slow arcs. Within this environment, NGC 4889 stands as one of the brightest and most massive members, sharing the central region with its neighbour, NGC 4874. A simple way to think about this scene is that the cluster is a vast valley of gravity. NGC 4889 is one of the great stones that has settled into its lowest part. The stars that give NGC 4889 its glow are not newly formed blue or restless. They belong mostly to old red populations, quiet, long-lived stars left after earlier eras of star formation have passed. This calm population hints that most of the galaxy's gas, the raw material for new stars, has already been used up or gently removed. At the scale of the cluster, the Coma environment adds another layer to this quiet story. Between galaxies, thin, hot gas fills the space, glowing in X-rays that show how deep the gravitational well truly is. Dark matter, unseen but measurable through motions and lensing, forms a massive halo that surrounds the cluster and guides the orbits of its galaxies. A calm summary of this stage is that NGC 4889 is not isolated but is embedded in a larger, heavier structure that supports its growth. Inside the galaxy, gravity shapes the paths of billions of stars into smooth, overlapping orbits. Some stars wander far into the outskirts, tracing the extended stellar halo, where the brightness drops to almost invisible levels. Others stay closer to the center, where small variations in motion already hint that something very massive sits buried deep within. Even without numbers or equations, it is enough to know that faster stellar motions near the center point toward more mass hiding there. Over long spans of time, smaller galaxies sink toward the center of the cluster, losing stars to tides and encounters. Those stars swell the faint outer envelope of central giants like NGC 4889, while their cores may sink inward and feed the central mass. The importance of NGC 4889 in this cluster story lies in its role as both product and participant. It is shaped by the deep potential well of the Coma Cluster. In turn, its central black hole and stellar body help stir and heat the surrounding environment. This feedback between galaxy and cluster is gentle when described in this way. It forms a quiet link between local stellar motions and the large-scale calm of the cluster's gas and dark matter. A simple restatement is that understanding NGC 4889 is a way to understand how dense regions of the universe evolve and settle. The black hole itself remains hidden, mentioned only as a hint within the motions of stars and the slight changes in light near the core. Later stages of the story will move inward from the wide cluster environment to the inner halo, and then toward the compact central region. Step by careful step, the smooth light profile, the slow rotation, and the high stellar speeds will come together. Together they show why astronomers infer such a massive dark heart. In simple terms, this first look establishes NGC 4889 as a calm central system within a crowded cluster environment. This calm beginning sets the tone for the rest of the journey. For this opening section, it is enough to hold a single soothing picture in mind. A vast rounded galaxy rests in the middle of a rich cluster, its stars moving in ordered patterns under the pull of gravity. That pull grows stronger toward an unseen perfectly dark center. NGC 4889 does not float in isolation. It belongs to the crowded city of galaxies known as the Coma Cluster. The core idea in this section is simple. The Coma Cluster is a deep gravitational basin where galaxies' gas and dark matter gather and slowly evolve together. In this setting, NGC 4889 becomes easier to understand as one piece of a larger structured environment. The Coma Cluster lies hundreds of millions of light-years away in the direction of the constellation Coma Berenices. It sits far beyond the reach of any single star system. Within its volume, hundreds of sizable galaxies drift, each carrying its own star's gas and dark matter halo. Together they move inside a much larger halo that wraps around the cluster as a whole. In calm terms, the Coma Cluster is a very massive region, where gravity has had a long time to pull matter inward. A soft mental picture shows countless galaxies as lights in a dim, three-dimensional web. Some are bright and round, like NGC 4889. Others are smaller and less regular. They follow paths that curve through the cluster's potential, much like leaves slowly swirling in a broad, nearly invisible whirlpool. The cluster does not sit in empty space. Between the galaxies, very thin gas fills the region heated to tens of millions of degrees and shining in X-rays. This hot atmosphere is called the intra-cluster medium, and it acts like a faint glowing fog that reveals where the cluster's gravity is strongest. When mapped, this gas piles up most strongly toward the center-wrapping galaxies like NGC 4889 in a broad diffuse bath. A single summary of this idea is that the Coma Cluster is not just a group of galaxies, but a shared pool of gas and gravity. Dark matter adds another layer beneath what light can show. It does not emit or absorb radiation. Its presence is inferred from the fast motions of galaxies and from the way the cluster bends background light. In simple language, the cluster is heavier than all its stars and gas alone would suggest. Dark matter forms a deep extended halo that shapes the paths of everything inside. Galaxies sink gently toward regions where this invisible mass is densest. Over time, some of them merge with central giants or pass close enough to lose stars into the cluster's common envelope. This slow, steady process makes the Coma Cluster a living, evolving structure rather than a static scene. NGC 4889 sits near the gravitational center of this whole arrangement. Its position means that it has likely experienced many close encounters and mergers. In a slow, calm sense, it is natural sink for material drawn down by the cluster's overall pull. As smaller systems and streams fall inward, they contribute stars to its outer halo, and perhaps gas and compact objects to its deeper layers. A quiet payoff of this view is that NGC 489 records the history of the cluster around it. Studying the cluster also shows why very massive black holes might be more common or more extreme in such environments. In dense regions, galaxies meet and interact more often. Gas is stirred, compressed, and sometimes driven toward the centers of galaxies. Over long times, this can feed central black holes and help them grow beyond the masses typical in quieter, more isolated systems. The Coma Cluster, with its rich population and deep potential, well offers exactly such a setting. NGC 4889, as one of its brightest central members, stands as a prime example of this slow cumulative growth. A gentle visual anchor focuses on the cluster core as a crowded but calm sky. Bright ovals and small smudges of light overlap, slightly stretched in subtle ways by mutual gravity and by the cluster's mass. In this quiet scene, NGC 4889 glows with steady light, while the hot gas around it forms an unseen high-energy sea. The cluster's combined gravity holds everything together from tiny dwarf galaxies to the massive central black hole that will be explored more closely later. Seen this way, the Coma Cluster becomes a framework that explains why NGC 4889 is both so massive and so important. It is part of a long chain that links dark matter, hot gas galaxy mergers, and black hole growth into a single, gently unfolding story. For a final calm thought in this section, the Coma Cluster serves as a bridge between individual galaxies and the cosmic web. Its great mass and clear structure allow astronomers to test ideas about gravity dark matter and the way matter collects over billions of years. In this balanced, dense environment, NGC 4889's central black hole can be seen as one outcome of long patient accumulation. The surrounding cluster holds the memory of that process in the distribution of galaxies' gas and unseen mass. With this wider landscape in place, the next step is to move inward. The focus shifts from the cluster as a whole toward the layered body of NGC 489 itself. NGC 4889 rests inside a much larger structure than its own starlight suggests, a deep halo of dark matter that belongs to the Coma Cluster. The simple idea in this section is that an invisible scaffold of mass surrounds the cluster and the galaxy, guiding their motions and shaping their growth. Dark matter in this calm description is matter that responds to gravity, but does not shine a hidden weight that quietly steers everything around it. Astronomers infer its presence because galaxies in the cluster move faster than visible mass alone can explain, and because background light bends as it passes by. In everyday terms, the Coma Cluster behaves as if it sits inside a vast transparent shell of mass. This shell is heavier and wider than the combined stars and gas it holds. Within this shared halo, galaxies drift like lanterns embedded in glass, their paths curved by a presence that cannot be seen directly. At the scale of the cluster, this dark matter halo provides the deep gravitational well that gives the Coma Cluster its identity as a bound system. Without it, the galaxies and hot gas would not remain gathered over billions of years. The hot intracluster medium, so thin that it would count as near vacuum on Earth, still traces this invisible structure. Where the halo is densest, the gas piles up more strongly, shining more brightly in X-rays. A gentle mental image forms of a glowing fog suspended in an unseen bowl, with galaxies like NGC 4889 settling toward its lowest parts. This picture makes the link clear between dark matter and the places where massive galaxies grow. On smaller scales, NGC 4889 sits inside its own dark matter halo nested within the greater cluster halo, like a smaller shell within a larger one. The galaxy's stars orbit not only the visible mass of other stars, but also this extended invisible component. In plain language, the dark matter halo of NGC 4089 adds extra gravity that holds onto distant stars and gently tugs on neighbouring systems. Over long stretches of time, this extra grip helps the galaxy collect material that passes nearby from small satellites to loose streams of stars. A quiet payoff of this view is that the smooth rounded form of NGC 4889 is not just a property of its stars, it is the outward sign of how both visible and invisible mass have settled together. The shape and extent of the dark matter halo also influence how gas falls toward the centre. They affect how easily that gas can cool and form new stars. In a cluster core, however much of the gas is kept hot by past activity and by the overall environment, so new star formation remains low. What continues instead is the slower process of dynamical evolution under gravity. Galaxies sink inward, orbits change, and the distribution of mass adjusts with each small interaction. The dark matter halo acts as a memory of this history, holding the combined result of many events in its smooth profile. A simple restatement is that the halo shows where matter has spent the most time. For NGC 4889, being close to the cluster center means that its halo blends with the cluster's own. There is no sharp boundary where one ends and the other begins. Instead, there is a gradual transition from the region dominated by the galaxy's mass to the broader region where the cluster's dark matter takes over. This smooth handoff of influence explains why central galaxies in clusters can grow so large. Their halos lie deep in the cluster potential, so infalling material finds it easier to remain bound to them. In a calm way, this continuous structure supports the growth of both the stellar body and the central black hole. The gravity of the halo shapes the orbits of stars that pass near the core. It controls how often they wander into regions where the central black hole's pull becomes important. Another soft visual anchor is a nested set of dim, overlapping spheres. The innermost region holds the black hole and the densest stars. Around it lies the luminous body of NGC 4889. Beyond that spreads the galaxy's dark halo, and beyond even that the broader halo of the Coma Cluster. Each layer influences the ones within, and together they define how matter moves from the outskirts down toward the center. In this layered scene, NGC 489 becomes more than a bright patch of stars. It is a node in a web of gravity shaped by a scaffold that remains unseen but strongly felt. As the story moves inward in later sections, this quiet background of dark matter stays in place. It supports the slow, steady growth of structures closer to the core. This view keeps the tone gentle because nothing here rushes or threatens. Over cosmic time, the scaffold changes only slowly while galaxies adjust within it. NGC 4889 and its dark heart simply continue to settle deep in the shared gravity of the Coma Cluster. NGC 4889 extends far beyond its bright central glow, wrapped in a faint outer stellar envelope that stretches into the deep core of the Coma Cluster. The idea in this section is simple and gentle. The galaxy carries a wide, diffuse halo of stars that preserves the memory of many past encounters. This envelope is so faint that in ordinary images it almost disappears into the sky background. Yet when astronomers reach deeper with long exposures and careful processing, a broad wash of light emerges around the central galaxy. It resembles a quiet mist of stars spread thin across hundreds of thousands of light years. In calm terms, this outer halo shows where the galaxy has touched and slowly absorbed other systems over time. Many of the stars in this extended envelope are thought to come from smaller galaxies that wandered too near the center of the cluster. Tidal forces pull them apart, stripping stars that then drift into long streams. Over billions of years, these streams stretch, overlap and blur into a smooth, low-surface brightness sea. The core of NGC 4889 sits like a brighter island in this wide ocean. A helpful way to picture it is as a soft gradient of light bright in the middle and gently fading outward until it merges with the general glow of the cluster core. In this setting, NGC 4889 no longer appears as a sharply bounded object. Instead, it blends with the intracluster light created by many disrupted galaxies. The boundary between galaxy and cluster becomes more a matter of definition than a strict physical edge. This makes the outer envelope a sensitive tracer of the cluster's dynamical past. If a region of the halo is slightly brighter in one direction, it can hint at a preferred flow of material. If faint shells or ripples appear, they can suggest more recent mergers whose debris has not yet fully mixed. The outer envelope therefore acts like a slow-moving record of gravitational events. A simple restatement is that this faint light remembers what the brighter inner galaxy has already forgotten. The stars in this region move under the combined pull of NGC 4889, the cluster's dark matter halo, and the nearby galaxies that share the core. Their orbits are long and often elongated, carrying them far from the center before gently turning them back again. Because these stars lie in the deep cluster potential, they are not easily lost. Even when they drift far from the central body, the overall gravity of the Coma Cluster calls them back. This steady confinement allows the halo to grow gradually as each new disrupted system adds its light to the whole. A quiet payoff of this understanding is that the outer envelope connects local and global scales. By studying its brightness and extent, astronomers gain clues about how many galaxies have fallen into the cluster core, how often they have merged, and how strongly the central region has been stirred. NGC 4889, as one of the main anchors at the center, stands near the focus of these flows. Its halo overlaps with the halos of nearby giants and with the diffuse intracluster light forming a complex layered structure. A gentle visual anchor is a very wide-field view of the cluster center. In this view, the brightest galaxies shine at the foreground of perception, while an almost imperceptible veil of light fills the spaces between them. Most of that veil consists of stars that no longer belong clearly to any single galaxy, yet many remain loosely associated with giants like NGC 4889. At night, if such a scene could be seen directly, it would look like a dim, pale fog of starlight with brighter knots embedded inside. The outer envelope of NGC 4889 is one of those knots fading gradually into the fog. This slow transition outward prepares the way for a later move inward. Just as the halo records the long history of accretion and disruption, the inner regions hold clues to how mass has settled closer to the core. In this quiet gradient from outermost halo to inner body, each radius carries a slightly different memory of past encounters and slow mixing. In a calm summary, the outer stellar envelope of NGC 4889 is a gentle extended glow that connects the galaxy to its environment. It shows that the galaxy has grown not in isolation, but through many small and large additions over cosmic time. It also shows that the Coma Cluster's core is a place where individual galaxies blend into a shared background of light. From this wide, soft halo, the narrative can now begin to narrow its focus. The next steps move down the brightness profile toward the main body, where the galaxy's structure becomes clearer, and the influence of its central dark heart slowly strengthens. NGC 4889 shows its character most clearly in the smooth glow of its main body, the region where most of its starlight gathers into a stable form. The simple idea in this section is that the bright core and surrounding luminous envelope follow patterns typical of a giant elliptical galaxy. These patterns give quiet clues about how mass and history are arranged. When astronomers measure how brightness changes from the center outward, they find a gentle, predictable decline rather than sharp features or sudden breaks. In calm language, the galaxy's main body behaves like a single continuous system rather than a collection of distinct parts. The light profile, which describes how brightness falls with distance from the center, often follows what is called a Cercic profile, a smooth mathematical curve that fits many ellipticals. For NGC 4889, this curve is steep toward the center and stretches far into the halo, showing that the galaxy holds a very concentrated yet extended stellar population. In simple terms, the core glows strongly, while the outskirts fade slowly, creating a broad, rounded shape that dominates the local cluster view. This structure matters because it tells how stars and mass are distributed, and it hints at how many mergers and interactions have been smoothed together over time. Seen in soft imagination, the main body is like a deep, luminous well of stars, brightest at the bottom and dimming gently along the walls. Within this well, stars move in many directions, their combined light blending into a single extended glow. Unlike a spiral galaxy which separates stars into a disk bulge and arms, NGC 4889 presents almost no internal pattern to the eye. There are no clear dust lanes, no bright knots of recent star formation, and no obvious rings. The absence of these features is itself a quiet message. It suggests that cold gas is scarce, that recent major inflows of fresh material are limited, and that the galaxy's main growth phase lies in the past. A calm summary of this scene is that NGC 4889 is a mature, relaxed system whose visible structure changes slowly. The stars that fill this main body belong largely to old populations. Their light is redder and steadier than the blue glow of young massive stars. Over time, heavier stars have already lived and ended their lives, leaving behind dimmer remnants. The remaining stars trace smooth orbits in the combined gravitational field of the visible and dark matter. These orbits, though individually complex when taken together, produce a stable, smooth density distribution. This is why the surface brightness appears so regular when mapped in detail. In the deeper central regions, the light profile may flatten slightly, forming what is known as a core where brightness does not continue to rise as sharply as expected. In simple language, the innermost region seems slightly underfilled with stars compared to an untouched profile. This subtle deficit can be a signal that past black holes or binary black holes have scattered stars outward, carving a shallow dip into the central light distribution. Even without technical detail, the important idea is that the way light rises and flattens toward the center quietly marks the influence of a massive dark object. A gentle visual anchor focuses on an image where the bright center of NGC 4889 glows like a blurred lamp. From that lamp, light fades through smooth shades of brightness with no sudden edge where the galaxy ends. Instead, the main body simply merges into the faint outer halo described earlier. This continuous transition emphasizes that the luminous body and the envelope are parts of one extended system. In such a system, the main body holds most of the visible mass, while the halo holds much of the memory of past accretion. Together they form a layered but still unified structure. For astronomers, modeling this light profile is a way to estimate the total stellar mass and to separate the contributions of stars' dark matter and the central black hole. For this gentle narrative, it is enough to know that the luminous body of NGC 4889 is both highly concentrated and widely spread, suggesting a long history of accumulation and smoothing. This history matters for the central black hole, because the same processes that gather stars into the core also bring gas and compact objects toward the center. Over cosmic time, this inward drift offers fuel and companions to the black hole even when dramatic events are rare. In a relaxed final thought for this section, NGC 4889's main body stands as the calm, glowing heart of the galaxy's visible structure. Its smooth profile, old stars, and extended reach show a system that has already done most of its growing. Inside this stable light, the influence of the dark central mass is present but not yet fully revealed. The next inward steps will look more closely at the inner regions where motions become more intense, and where the quiet signals of the black hole begin to stand out more clearly against the surrounding stars. NGC 4889 carries the marks of a long history of mergers, even though its present form looks smooth and regular to distant eyes. The simple idea is that many separate galaxies have combined to build a single, massive elliptical body with a dense central region. Over time, these mergers have erased sharp structures while still leaving quiet clues in the motions and distribution of stars. In gentle terms, the galaxy that appears as one object today is really the blended outcome of many earlier systems that have fallen together inside the Coma Cluster. When smaller galaxies fall toward the cluster center, they move through the deep gravitational well shaped by dark matter and the combined mass of central giants. Their orbits slowly decay as they lose energy through tidal interactions and encounters. As they come closer to NGC 4889, tidal forces stretch them, loosening stars from their outer parts first. These stripped stars spread into streams and shells that eventually fade into the outer halo. The compact central regions of the infalling systems sink further inward, where they can merge more completely with the host galaxy. In this slow way, repeated mergers add mass to the main body and help build a rounded, bulge-like central structure. A calm way to picture this is to imagine a series of smaller, bright knots sinking into a broader pool of starlight and slowly dissolving into it. The resulting central region holds stars from many origins, all moving under the combined pull of visible and invisible mass. In the case of NGC 4889, careful measurements of its light and kinematics support a story of such cumulative growth rather than simple isolated formation. The galaxy behaves as a classic slow rotator with limited overall spin and strong random motions. This pattern usually points toward a history dominated by major and minor mergers instead of steady, quiet gas accretion. A gentle summary is that collisions and unions have done most of the shaping. In the central regions, where the light rises steeply, the stellar distribution forms something like a massive bulge. In spiral galaxies, a bulge sits in the middle of a disk and often rotates more rapidly. Here, in a giant elliptical, the central density peak plays a similar structural role without a surrounding disk. It acts as the main luminous anchor for the galaxy, concentrating much of the stellar mass into a compact zone. Within this zone, random stellar speeds are high, and the gravitational field changes quickly with radius. This is also the region where the central black hole's influence begins to matter, even if its presence is not yet obvious in simple images. Another soft visual anchor focuses on the inner tens of thousands of light-years around the center. In that mental image, countless stars move on intersecting paths, like slow, glowing grains drifting in a deep bowl. None of the orbits stands out to the eye, but together they create a steady brightness that peaks at the center. Slight twists or asymmetries left over from earlier mergers may still be present, yet they are subtle, visible only through careful analysis. Over time, gravitational interactions between stars and the overall potential help to smooth these irregularities. The central structure grows more rounded and more regular, even as it keeps the memory of past events in its internal motions. This steady smoothing process explains why NGC 4889 now appears so calm. From a distance, it shows almost no obvious scars from the many collisions that likely built it. Yet the very existence of such a massive, centrally concentrated system in the crowded core of Coma strongly suggests that these events have occurred. In soft terms, the galaxy is a settled outcome of long-past activity. The importance of this merger-built bulge-like structure reaches beyond the stars alone. As each infalling system arrives, it can bring gas star clusters and compact remnants. Some of this material may be directed inward toward the very center, where it can feed or interact with the central black hole. Even if the current galaxy looks quiescent, the accumulated effect of many such deliveries over billions of years can help drive the black hole to extreme masses. For this reason, the shape and mass of the central region act as quiet indicators of what the dark heart at the core may be like. In one calm sentence, the central luminous structure and the black hole form a linked pair, each shaped in part by the same long record of mergers. As the narrative moves yet further inward, this connection becomes clearer. The focus shifts from the general form of the central body to the detailed motions of stars in the innermost regions. Their changes in speed and direction provide direct evidence for the heavy invisible object that rules the very heart of NGC 4889. Deep inside NGC 4889, the starlight thickens into a compact nuclear region where gravity grows steep and the galaxy's history feels more concentrated. The simple idea in this section is that the nuclear zone forms a bridge between the broad luminous body and the central black hole holding dense stars and subtle signs of past activity. Within a few thousand light years of the center, the brightness rises more sharply, and stellar motions become more complex. In calm language, this is the region where the galaxy's structure narrows, and its behavior begins to change. Here stars crowd together into a dense swarm. Their orbits twist and turn in many directions, influenced by the combined pull of the central stellar mass, the dark matter background, and the unseen black hole deeper in. The nuclear region can sometimes hold a distinct nuclear star cluster, a dense gathering of stars very close to the center. In a galaxy like NGC 4889, any such cluster would blend into the bright central light, but its presence or absence still matters. It tells how material has flowed inward over time, and how star formation and black hole growth have shared the same narrow space. A gentle way to picture this area is as a glowing knot of light inside the broader galaxy. In that knot, the density of stars rises and the scale of motion shrinks. Distances that once measured tens of thousands of light years outside now shrink to only a few thousand or even a few hundred. Within these smaller volumes, changes in gravity show up more clearly in how stars move. A calm summary is that the nuclear region is where tiny shifts in mass distribution have large effects on orbits. The light profile in this central zone sometimes shows a shallow dip or flattened core, hinting that stars have been removed from the very center. One gentle explanation is that past interactions with one or more massive black holes have scattered some stars outward, leaving a slightly less crowded inner pocket. Even this small adjustment carries important information. It suggests that the nuclear region has not remained static, but has felt the influence of a growing, perhaps once binary dark heart. In more active times, gas may have reached this region and settled into disks or rings before sinking further in. That gas could briefly feed a bright active nucleus, turning the center into a quasar-like source before the supply thins and the light fades. Today, NGC 4889 appears largely quiet, with no strong jets or bright central outburst visible. Yet the nuclear region still holds the record of those possibilities in its structure and motions. Another soft visual anchor centers on a narrow field around the core. In this view, the outer galaxy fades from attention, What remains is a small, intensely bright area where individual stars blur into a smooth central glow. Beneath that glow, stars orbit at high speeds along intricate paths. Some follow nearly circular loops, others trace elongated or tilted routes. Together they form a thick, slowly turning swarm. The central velocity field, when measured, may show slight twists or asymmetries, perhaps suggesting a rotating component or a faint ring. In everyday terms, the nuclear region behaves like a crowded stellar city, where no single motion dominates, yet the overall pattern still reflects the hidden weight at the centre. This nuclear zone also acts as a meeting ground for material arriving from different directions. Small galaxies that spiral inward can deposit their remaining cores here. Star clusters on sinking orbits can dissolve into the background light, adding their stars to the general mix. Gas drifting down from larger radii can form short-lived disks and form stars before being stirred or heated again. Over long periods, these processes blur into a gentle average, but their cumulative effect is a dense, centrally concentrated population. A simple restatement is that the nuclear region collects and blends whatever the rest of the galaxy and cluster send inward. This collection matters for the central black hole, because it sets the conditions in its neighbourhood. The density of stars determines how often close encounters and captures can occur. The flow of gas controls how often the black hole can accrete enough material to flare brighter. Even when no current outburst is visible, the arrangement of mass around the centre shows whether such feeding has likely happened before. In NGC 489, the combination of dense nuclear light, high stellar speeds, and hints of a central core all point toward a history in which the black hole has already played an important role. For this calm stage of the journey, it is enough to recognize the nuclear region as a layered, dynamic environment. It is neither as simple as the outer halo, nor as hidden as the black hole's horizon. Instead, it forms a transitional zone where observable stars respond directly to the strong gravity near the center. As later sections move even closer in, they will follow the motions of these stars more precisely, using their speeds and directions to weigh the dark heart that organizes this quiet, crowded core. NGC 489's nuclear region does more than simply shine. It also moves in complex layered ways that quietly reveal how disturbed its inner history has been. The simple idea in this section is that the patterns of stellar motion near the center show where the galaxy has been gently shaken by past events. When astronomers examine this region with detailed spectroscopy, they do not only measure how bright it is, they also measure how quickly stars move toward and away from the observer, building a map of speeds across the core. In calm language, this map of motion is like a slow weather chart for stars showing patches of higher and lower stellar winds inside the galaxy. Near the very center, the average speeds of stars along the line of sight become very high. They do not all rush in a single direction. Instead, their velocities spread across a wide range. This spread in speeds hints at the presence of a very massive central object, but it also records the way mergers and interactions have stirred the inner galaxy. In some zones, the line profiles of starlight become skewed or broadened in unusual ways, as if multiple families of orbits overlap in the same region. A gentle visual anchor focuses on a small patch around the core, where each tiny piece of the image holds stars moving at slightly different speeds. Together they form a smooth glow, but underneath that glow their motions weave a more intricate pattern. In an ideal, completely relaxed system, stellar motions might be nearly symmetric in every direction. In NGC 489, the observed kinematics suggest more structure. There may be signs of a slowly rotating component, or of an elongated collection of orbits forming something like a weak hidden ring. Some studies even hint at an eccentric torus of stars, a thick off-center arrangement that circles the core on elongated paths. In simple terms, the stars near the center do not all follow the same smooth pattern. Their motions overlap, twist and tilt, reflecting the layered way the galaxy has assembled its mass. This complexity matters because it affects how the central black hole's influence is measured. When astronomers model the motions of stars to weigh the dark heart, they must account for rotation asymmetry and any substructures. If they ignored these details, they might misread how much of the motion comes from the black hole and how much comes from the way stars are arranged. A calm summary is that the inner few thousand light-years of NGC 4E89 contain both the signature of the black hole and the lingering echo of past rearrangements. Another way to picture this region is as a crowded three-dimensional net of stellar orbits. Some orbits are nearly circular, carrying stars around the center, like beads on a smooth loop. Others are elongated, plunging closer to the core before sweeping back out again. Still others may be tilted, forming a thick, slowly twisting structure around the central mass. The overall effect is like many overlapping currents in a deep, still pool. On the surface, everything appears calm. Below the surface, the currents trace a layered and evolving history. Over cosmic time, relaxation processes slowly reduce the sharpest disturbances, but some patterns remain. In the case of NGC 4889, any eccentric torus or asymmetric feature may be a fossil of an earlier phase, when gas disk star formation or mergers imprinted structure onto the nuclear region. These features do not threaten the galaxy's stability. Instead, they provide extra information. They show that even a very massive, apparently settled system can hold fine structure at its core. For the central black hole, this environment sets the stage on which its gravity acts. Stars on elongated orbits may pass relatively close to the center, entering the zone where the black hole's pull dominates. Others remain farther out, feeling its influence only as a general deepening of the central potential. The distribution of these orbits helps determine how mass is packed around the core, which in turn affects the shape of the velocity distribution that astronomers observe. A simple restatement is that the dark heart shapes the dance, but the dancers also record how the stage was built. As the narrative continues, inward attention turns from the detailed geometry of these motions to a single very useful number. That number is the velocity dispersion, a measure of how widely star speeds are spread around their average. In the next step, this quantity becomes a key bridge between what is seen in starlight and what is inferred about the hidden mass at the center of NGC 4889. This gentle shift in focus from detailed patterns to a single statistical measure keeps the picture manageable. It allows the complex inner motions to be summarized without losing their connection to the galaxy's deep gravitational core. With that tool in hand, the story can now move one step closer to weighing the dark center itself. Velocity dispersion becomes a key guide inside NGC 4889, turning complex motion into a single calm measure of how strongly gravity holds the central stars. The simple idea in this section is that a wider spread in stellar speeds points toward a larger mass hidden in the core. Velocity dispersion is the spread of star speeds. In this gentle context, that spread summarizes many individual orbits into one number that still carries the imprint of the dark heart. When light from the galaxy's center is split into its colors, spectral lines broaden, because stars move at slightly different speeds along the line of sight. Some stars drift toward the observer, others drift away, and many move at angles between. Their combined motion produces a smooth line that is thicker than it would be in a still system. The width of this line gives the velocity dispersion, and with it, a first sense of how deep the central gravitational well must be, A calm summary of this idea is that faster and more varied stellar motion means stronger gravity, and therefore more mass. In NGC 4889, measurements show that the velocity dispersion in the central region is very high. Stars near the core move at hundreds of kilometers per second, not along a single organized stream but as part of a crowded swarm. This widespread in speeds does not make the galaxy unstable. Instead, it allows the system to remain supported against collapse by orbital motion rather than by pressure. In astrophysical language, the galaxy is pressure supported, but in this quiet story it is enough to say that random motions keep the structure balanced. A soft visual anchor focuses on countless stars around the center, each tracing its own slow path. Some loop closer in where gravity is stronger and speeds rise. Others wander farther out on more extended orbits. At any given moment, some stars move inward, some outward, and many sideways, yet the overall pattern stays steady. The velocity dispersion is the gentle statistical description of this busy dance. What matters most for the dark heart is how this dispersion changes with distance from the center. Far from the core, stellar speeds may be high, but relatively uniform, reflecting the total mass of stars and dark matter. Closer in, if there is an additional compact mass, the dispersion tends to rise. In NGC 4889, observations indicate that the inner region shows such a rise consistent with a massive central concentration. In simple terms, the stars near the core move too fast to be explained by starlight alone. This mismatch is a quiet but powerful clue that an enormous black hole sits at the center. To turn these clues into estimates of mass, astronomers build models that combine the galaxy's light profile, its possible orbital shapes, and the observed dispersion. They adjust the amount of central dark mass until the model matches the measured widths of spectral lines at different radii. The details of these models are intricate, but the outcome is conceptually straightforward. In NGC 4889, the best-fitting models point to a black hole mass of many billions of suns. A simple restatement is that only a very heavy central object can sustain the observed spread of stellar speeds without tearing the galaxy apart. Even with careful modeling, there remain uncertainties. The exact orbital mix, the influence of dark matter, and the quality of the data all play roles. In a gentle narrative, this means that the final number carries a range rather than a single rigid value. Still, the overall conclusion is robust. Whatever the precise figure, the central black hole in NGC 4889 ranks among the most massive known. This realization carries a soft sense of significance. It shows that cluster center galaxies can host black holes far larger than those in more typical galaxies. It also supports the idea that dense environments, frequent mergers, and long periods of gentle feeding can drive black hole growth to extreme scales. The velocity dispersion curve rising toward the center becomes a quiet signature of this long history written into stellar motion. For those looking at the cluster as a whole, this has further meaning. A black hole of such mass can influence how gas behaves near the center over cosmic time, even if it appears calm now. Energy released during past active phases would have moved through the surrounding medium, heating and stirring the gas. In the present, the memory of this influence may remain in the structure of the hot intra-cluster atmosphere. In one last soft thought for this section, velocity dispersion offers a way to hear the silent pull of the dark heart. By listening to how fast the stars move, even without seeing the black hole itself, the depth of the central well becomes clear. From here, the story can move from these statistical hints toward a more direct picture of how mass piles up near the core of NGC 4889. In later steps, that concentration will be linked gently to the wider galaxy and cluster. In NGC 4889, the evidence from light and motion gathers toward a simple conclusion: mass, becomes ever more concentrated as the center is approached. The guiding idea in this section is that stars' dark matter and an enormous black hole together build a steep gravitational core. This core shapes how orbits behave and how the whole galaxy holds its form. In calm language, the closer the view moves inward, the more clearly the weight of the dark heart is felt. The stellar light profile already hints at this. It rises sharply toward the center and then gently flattens in the innermost region, as if some stars have been moved outward. That faint central deficit compared to a smooth inward extrapolation suggests that past black hole activity or black hole mergers have scooped stars from the very center. Even without focusing on details, the key point stays soft and clear. The visible stars do not fill the core as tightly as simple models would expect, so something heavy and compact has likely rearranged them. Around this region, the velocity dispersion also climbs. Stars move faster and follow more tightly curved paths, responding to a steeper gravitational potential. The combination of high dispersion and a scoured, shallower core indicates that a large fraction of the central mass is packed into a region much smaller than the visible light suggests. In gentle terms, the mass profile outpaces the light profile, pointing strongly to a hidden central concentration. Astronomers describe this by saying that the mass-to-light ratio rises toward the center. In everyday words, each unit of starlight near the core corresponds to more mass than in the outskirts. Some of this extra mass may be in faint stellar remnants. Some may be in dark matter that reaches inward, but the dominant part is thought to be the supermassive black hole whose event horizon lies deep inside. A soft visual anchor imagines a series of nested shells within NGC 1889. The outer shells hold stars and dark matter distributed fairly broadly. Moving inward, each shell encloses more mass than one might expect from the light, until the innermost shells wrap tightly around a point-like invisible object. The result is a steep central well, a region where gravity changes very quickly across small distances. For stars on orbits that pass through this zone, even a small inward move brings a strong increase in speed. Over time, these orbits help define the inner structure. Some stars are flung outward after close encounters with the central mass or past black hole pairs. Others settle into tighter paths that circle the core. In this way, mass not only sits in the center, but continuously reshapes the surrounding region. A calm summary is that the central few hundred light-years of NGC 4889 are dominated gravitationally by a single compact source. The larger galaxy acts mainly as a backdrop there, providing the environment that delivered material to this dark heart. This concentration has further consequences for how the galaxy and cluster behave together. A very massive central object can influence how gas flows in the core of the Coma Cluster. Even if the black hole is quiet now, its past outbursts would have pushed on the hot intracluster gas. Jets and winds from earlier active phases may have carved cavities, stirred turbulence, and helped keep the gas from cooling too quickly. The current steep mass profile is therefore not just a local feature. It connects to the long-term thermal balance of the cluster's core. In soft language, the weight at the center of NGC 4889 has helped set the temperature and structure of the surrounding medium. From the perspective of cosmic structure, this deep concentration of mass in one galaxy shows how gravity can pile matter into very small regions without disturbing the large-scale calm. The cluster remains a stable, slowly evolving system, even while its central galaxy hides an extreme density in its core. On human terms, such scales and densities are difficult to picture, so the narrative remains slow and gentle. Instead of focusing on numbers, it rests on the contrast between the wide, luminous body of the galaxy and the tiny region that holds most of its deepest gravity. This contrast carries a quiet reassurance. The vast majority of stars in NGC 4889 orbit safely at great distances following stable paths that barely feel the full force of the central mass. Only a small inner volume lies under the most intense influence. With this layered view in place, the way is prepared for a broader comparison, where NGC 4889's concentrated core is set alongside black holes in other massive galaxies. The task of weighing the dark heart of NGC 4889 begins with the motions of its stars. Those motions are not treated as isolated paths but as traces of gravity. The central idea in this section is that careful models of these motions reveal how massive the hidden black hole must be. By turning light into measurements of speed and direction, astronomers test different mass distributions and see which one allows the stars to move as observed. In calm terms, the galaxy becomes a quiet laboratory, and its stars act as test particles drifting through a shared gravitational field. The basic ingredients of this method are simple to state. First, the brightness profile of NGC 4889 shows how many stars lie at each distance from the center. Second, the spectrum at each point shows how fast those stars move along the line of sight and how widely their speeds are spread. Third, a model combines the three-dimensional distribution of stars' dark matter and a central point mass to predict what the spectra should look like. The model then adjusts the mass of the black hole until its predictions match the measured velocities in a smooth and consistent way. A soft summary of this process is that the unseen mass is tuned until the simulated galaxy behaves like the real one. In practice, the modelling uses families of orbits rather than simple circular paths. Stars in NGC 4889 follow many kinds of trajectories. Some are elongated, some nearly round, and some are tilted out of the main planes. The model includes a large library of these possible orbits. Each orbit is allowed to carry a small fraction of the total light. By mixing them in different proportions, the model recreates the observed brightness and velocity patterns. The presence and mass of a central black hole determine which combinations are allowed. If the black hole mass is set too low, stars in the innermost regions cannot move as fast as the data require no matter how the orbits are mixed. If the black hole mass is set too high, the central speeds become excessive and the predicted spectra no longer match the observations. This quiet tension between too little and too much mass pins down a range of acceptable values. In NGC 4889, that range lies at extreme scales, with best estimates near tens of billions of solar masses. A gentle way to feel this is to imagine a black hole so heavy that its event horizon would reach far beyond the orbit of Neptune. Even with such weight, the galaxy remains calm. Only the innermost stellar motions know the full strength of the dark heart. Farther out, the combined mass of stars and dark matter dominates, and the details of the central object fade into a smooth background pull. The important message is that the inner kinematics demand a central mass far higher than any cluster of stars could provide. Alternative explanations, such as a swarm of dark stellar remnants, would struggle to reach the required density and stability. A single, supermassive black hole remains the simplest and most robust solution. The models provide not just a mass, but also an estimate of uncertainty reflecting limits in the data and in the assumptions about orbits and dark matter. In a calm narrative, this means that the exact number may shift as methods improve, yet the conclusion that the black hole in NGC 4889 is enormous stays firm. The galaxy joins a rare class of systems where central black holes reach the top end of the known mass range. This has a gentle but important consequence for how scaling relations are understood. Relations between black hole mass and galaxy properties such as stellar velocity dispersion, or bulge luminosity were first measured in more moderate systems. At the high mass end, galaxies like NGC 41889 show that these relations may bend or broaden. The dark hearts of brightest cluster galaxies may grow faster than simple trends, fed by rich merger histories, and the deep gravitational wells of their clusters. In simple words, NGC 44889 suggests that environments matter for how big a black hole can become. One can hold two calm images in mind. A small spiral galaxy may host a modest central black hole that follows common scaling laws. A giant cluster galaxy like NGC 4889 may carry a black hole so massive that it pushes those laws to their limits. Richer surroundings and deeper wells give more chances for gas and stars to drift inward over time. In one soft sentence, NGC 4889 teaches that the universe allows some black holes to grow beyond ordinary expectations in quiet central galaxies. With the mass now roughly weighed, attention can gently shift from what the black hole is to what it does. Later sections will look at how such a heavy object may have influenced the hot gas around it, and the slow evolution of the Coma Cluster's core. Through all of this, the black hole itself remains unseen, revealed only through its steady pull on light and motion. NGC 4889 does not only reveal an enormous black hole, it also sits at an interesting place among the general patterns that link black hole mass and galaxy size. The simple idea in this section is that astronomers compare many galaxies and find quiet trends, then notice how central cluster giants like NGC 4889 push those trends toward their edges. In ordinary massive galaxies, the mass of the central black hole tends to rise in step with the stellar mass or brightness of the central bulge. Brighter bulges and higher stellar velocity dispersions usually go along with heavier black holes, forming relationships that look like smooth sloping bands on a chart. These relationships suggest that galaxies and their central black holes grow together, sharing gas mergers and time in a balanced way. A calm summary is that bigger galaxies tend to hold bigger black holes, and the scatter around this rule is modest for many systems. NGC 4889 fits within this picture but leans toward the extreme upper side. Its main body is very bright and massive as expected for a brightest cluster galaxy. Its stars move with high velocity dispersion, again matching a system deep in a cluster core. Yet the inferred mass of its central black hole appears to sit near the top of what those relations would predict, or even above them. This means that for its brightness and dispersion, the black hole is unusually heavy. In gentle language, the dark heart of NGC 418 seems to have gained more weight than simple scaling would suggest. This is not a sharp break with the rules, but a quiet bending of them at the highest masses. When astronomers include other central cluster galaxies with very massive black holes, a pattern begins to emerge. The scaling relations that work well for smaller and mid-sized galaxies appear to curve or broaden at the top end. Brightest cluster galaxies sometimes host black holes that are heavier than expected from a direct extension of the usual trends. One possible explanation is that these galaxies have enjoyed especially rich growth histories. Sitting at the centers of deep potential wells, they experience more frequent mergers and continued infall of material. Over billions of years, this setting can funnel more gas and more compact systems toward the center where the black hole waits. Another possibility is that feedback from such massive black holes, once active, regulates their environment in ways that differ from normal galaxies. Powerful outbursts may heat surrounding gas and limit further star formation, while still allowing the black hole to grow during earlier brief phases. As a result, the final galaxy may reach a point where its stars grow only slowly, while its central mass has already passed the usual mark. In simple terms, the black hole may finish growing before the visible galaxy reaches an equivalent scale. NGC 4889 can be seen as one of these nearly finished systems. Its stellar population is old. Its star formation rate appears very low. Its structure is smooth and relaxed. All of these signs point to a galaxy that has nearly completed its visible growth. The central black hole, however, already stands at an extreme mass, as inferred from the inner kinematics. The galaxy therefore gives a gentle example of what happens when a system evolves long enough in a rich environment. The black hole grows quickly early on, then the surrounding stars settle into a stable form that changes only slowly. In the context of the Coma Cluster, this behavior carries extra meaning. If central black holes in brightest cluster galaxies are commonly overmassive relative to simple scaling laws, they may play a particularly strong role in regulating cluster cores. Their energy output in past active phases could have been enough to heat large volumes of gas, keeping the intracluster medium hot and extended. This would affect how quickly gas can cool and sink, and how many new stars can form in central galaxies like NGC 4889. A calm restatement is that the largest black holes may help keep their surroundings in a long-term gently balanced state. For those looking at the bigger picture of cosmic structure, NGC 4889 then becomes more than a curiosity. It stands as a test of how universal the usual galaxy-black hole relations really are. By sitting near or above their upper edge, it reminds researchers that simple lines drawn through data have limits. At the highest masses and in the densest environments, new factors appear. In this light, the position of NGC 4889 on a scaling diagram is not an outlier to be discarded, but a quiet signal that the story of coevolution has extra chapters. With this wider view in place, the narrative can shift back from charts and averages to the local environment. The next section turns to the hot gas that fills the core of the Coma Cluster, and to the slow, gentle ways in which a heavy black hole may have stirred and heated that gas over time. NGC 4889 sits inside a pool of hot gas that fills the core of the Coma Cluster, a thin atmosphere glowing softly in high-energy light. The simple idea here is that the central black hole, even when quiet, helps stir and gently heat this gas over long spans of time. This hot medium called the intracluster gas is so diffuse that it would count as near-perfect vacuum by everyday standards. Even so, it carries most of the normal matter between galaxies in the cluster core. Its temperature reaches tens of millions of degrees, so its atoms move very quickly and emit X-rays that observatories detect as a smooth extended halo. In calm language, the Coma Cluster holds a vast invisible furnace that stays hot without boiling over. The presence of hot gas matters because left entirely alone it would lose energy and begin to cool and sink toward the cluster center. As it cooled, it would condense, form clouds, and eventually feed new bursts of star formation in galaxies like NGC 4889. Observations show that the gas in Coma does not cool and condense as fast as simple calculations predict. There must be gentle heating sources that return energy to the gas and slow its inward flow. A quiet way to state the core idea is that feedback from central galaxies and their black holes helps maintain a long-term balance. In many clusters, signs of this feedback appear as cavities and ripples in the X-ray images of the gas. These are thought to form when jets or outflows from active galactic nuclei push aside the hot medium carving bubbles that then rise and mix. Even when the jets have faded, the structure of the gas remembers their influence in gentle ripples and subtle gradients. In the Coma Cluster, the picture is somewhat simpler and more diffuse, but the basic principle still applies. Energy released near the centers of massive galaxies, including NGC 4889, can spread outward into the intracluster medium. This spreading may occur through weak shocks, soft sound waves, or buoyant bubbles that transfer energy without violent disruption. A calm summary is that the gas receives small repeated pushes rather than a single dramatic event. Over billions of years, these pushes help keep the gas at high temperature, preventing it from collapsing rapidly into the cluster core. In this view, the black hole in NGC 4E89 plays a role out of proportion to its size. As matter occasionally accretes onto it, gravitational energy converts into heat radiation and sometimes mechanical outflow. Even if the black hole is not strongly active, now earlier phases of activity could have contributed significantly to the energy budget of the core. The galaxy sitting deep in the cluster potential serves as an efficient channel for energy from the small central region to the much larger volume around it. A gentle visual anchor imagines the hot intracluster gas as a faint glowing lake surrounding NGC 4889 and its neighbours. Occasional outbursts from central black holes send waves through this lake, smoothing temperature variations and slowing any tendency for the gas to cool and sink. Nothing in this picture needs to be violent. The gas remains hot and thin, and the galaxies continue their slow orbits within it. The balance between cooling and heating is not perfect, but it is good enough to shape the long-term evolution of the cluster. This balance matters because it influences how much fresh gas reaches the central galaxies and how many new stars can form there. In an environment where heating keeps pace with cooling, star formation stays low and steady. That matches the observed old stellar populations in NGC 4889. The galaxy's quiet red light suggests that it has not received large amounts of cool gas for a long time. Its central black hole and the broader cluster environment cooperate to maintain this calm state. Another soft way to state this is that the Coma Cluster core lives in a slow, controlled exchange of energy. Gravity tries to draw gas inward, while feedback from galaxies and black holes pushes energy outward. Somewhere between these tendencies, a gentle equilibrium emerges. NGC 4E89, with its immense dark heart, is one of the key participants in this process. From the perspective of cosmic structure, this gentle heating is not a minor detail. It helps decide whether clusters grow bright central starbursts or remain dominated by old stable galaxies. In Coma, the second path appears to have won. The hot gas stays aloft, the central galaxies remain quiescent, and the cluster core presents a calm, steady glow. With this broader environmental role of the black hole in mind, the narrative can move inward once again. The next stage returns to a much smaller scale, focusing on the region close to the event horizon. In that inner zone, space-time curves sharply, and direct observation gives way to careful inference. Near the very centre of NGC 4889, the view finally reaches the region where the central black hole's gravity dominates every other influence. The simple idea in this section is that close to the event horizon, space-time curves so strongly that ordinary intuition no longer works, yet the scene can still be described calmly from a safe distance. The black hole itself remains invisible. No surface, no solid edge, and no light emerge from inside its horizon. What can be described is the behaviour of matter and light just outside this boundary, in the narrow zone where the dark heart exerts its strongest pull on the galaxy. In this region, stars that venture too close feel intense tidal forces. Their far sides and near sides experience slightly different gravitational pulls, which can stretch and distort their orbits. Most stars in NGC 4889 never come this close. They stay on wider paths where the galaxy's total mass gently guides them. A small fraction, however, may travel on highly elongated orbits that bring them into the deep core. For those rare stars, a close passage can change the path forever, either tightening it into a more bound loop or slinging the star outward to new regions of the galaxy. Gas behaves differently. Unlike stars, which remain compact and collisionless, gas clouds can compress heat and radiate energy as they approach the center. If enough gas reaches the neighborhood of the black hole, it tends to settle into a flattened structure, an accretion flow where material spirals inward. Friction within this flow heats the gas, causing it to glow across the spectrum. In earlier times, such a structure near the black hole of NGC 4889 may have turned the nucleus into an active quasar. Today the galaxy appears quiet, which suggests that any remaining accretion proceeds slowly and gently if at all. In a soft mental image, the region close to the black hole is mostly dark, with only occasional faint streams of gas drifting inward and warming as they fall. Light passing through this domain follows curved paths. Gravitational lensing bends rays that come near the black hole, slightly distorting the apparent positions of background stars and gas. In principle, an observer with perfect instruments could detect arcs and halos shaped by this bending subtle signs that space itself is being curved by the central mass. In practice, at the distance of the Coma Cluster, and with current technology, these fine details remain hidden. They form part of the imagined rather than directly imaged structure of the inner core. In simple terms, the region near the horizon is known more by theory and indirect evidence than by direct sight. The size of this influence zone grows with the black hole's mass. For a black hole as heavy as the one in NGC 4889, the event horizon would span a volume larger than the orbit of the outer planets in the solar system. Around it lies a somewhat larger sphere where orbital periods become very short. Matter circling at these radii can complete a full orbit in times measured in days or hours. Even so, from the perspective of the galaxy, these motions remain tiny and distant. The rest of NGC 4889 turns slowly over millions of years, while the immediate environment of the black hole moves with far greater speed. Time itself behaves differently near the horizon. General relativity predicts that clocks close to the black hole run more slowly compared with clocks far away. For an outside observer, infalling material seems to slow and fade as it nears the event horizon, never quite crossing it in finite time. From the point of view of the infalling material, however, the passage through the horizon occurs in finite proper time with no sudden physical barrier. In this narrative, the focus stays on the outer description. The event horizon becomes a calm dividing surface in the story, a boundary beyond which the script does not need to speculate. This restraint keeps the description grounded in what can be related to observations and tested theory. It also keeps the tone gentle, because nothing in this region reaches outward to disturb the galaxy on human scales. Occasionally one can imagine a star wandering too close and being torn apart by tidal forces. The debris of such a disruption would form a bright brief flare as it spiraled inward and heated up, lighting the core for a short time. Events like these are rare and spread over long periods. They remind that even in a quiet galaxy, the central black hole can still awaken in brief episodes of activity. For most of its life, though, the dark heart of NGC 4889 likely remains in a low steady state, quietly holding its surrounding orbits in place. In this peaceful description, the region near the central black hole acts as the final sink for the long history of accretion and mergers that has shaped the galaxy. All flows of gas and compact objects that reach this inner zone eventually cross the horizon and vanish from view, leaving only their gravitational effect behind. The rest of NGC 4889 continues to orbit calmly around this point-like anchor, and the Coma Cluster continues to cradle the galaxy within its wider potential well. With the view now brought as close to the black hole as observation and theory reasonably allow, the story approaches its natural limit. The final step of the journey will not try to look deeper inside. Instead, it will stand at the edge of knowable description, gathering the layered perspectives of cluster, galaxy and core into one quiet picture of a dark heart that can be weighed and felt but not directly seen. In NGC 4889, the journey inward reaches a natural resting place at the edge of description, where observation and theory meet and then grow quiet. The guiding idea in this final section is that the galaxy, its cluster, and its dark heart form one layered structure that can be understood without crossing the event horizon. From the outermost halo of the Coma Cluster down to the inner core, gravity gathers matter, smooths away sharp features and leaves behind patterns that change only slowly over cosmic time. In calm language, NGC 4689 is a settled outcome of this long process, anchored by a central black hole whose presence is felt everywhere but seen nowhere. Far out in the cluster, galaxies drift through the shared dark matter halo, and hot gas fills the spaces between them. Their slow orbits and the wide glow of X-rays show how heavy and extended the cluster is. Closer to the center, brightest galaxies like NGC 4889 take on a special role. They sit near the bottom of the gravitational well, holding large fractions of the cluster's stars and acting as channels through which energy from central black holes reaches the intracluster medium. The Coma Cluster becomes easier to picture as a deep basin where matter has settled, with NGC 4889 glowing near the basin's lowest point. Within the galaxy itself, the outer envelope of faint stars blends almost seamlessly into the intracluster light. These stars remember the many systems that have fallen in and been gently shredded by tides. Moving inward, the main body of NGC 4889 brightens smoothly, showing a mature elliptical structure built through repeated mergers. Each layer of the galaxy and cluster has had time to relax into a calm, rounded form. In the inner tens of thousands of light years, the nuclear region gathers old stars and subtle signatures of past encounters. Slight twists in stellar motion, hints of rings or tori, and the gentle flattening of the central brightness profile all suggest that the center has been reshaped by a very heavy object. The velocities rise, the orbits become more tightly curved, and the mass-to-light ratio climbs, yet the overall picture remains one of balance. Stars find new orbits instead of being lost from the galaxy. The region simply adjusts around the growing central mass like a calm lake, reshaping around a slowly deepening hollow in its bed. Closer in still, the influence of the black hole becomes the dominant factor. The event horizon itself stays invisible, but its gravity sets the scale of motion in the deep core. Stars that pass nearby follow sharply bent paths. Gas that drifts inward can heat, glow, and then vanish across the horizon. For NGC 4889, these processes have likely happened many times over its long life. Short episodes of activity may have lit the nucleus, launched gentle outflows, and sent waves through the surrounding hot gas. Between those episodes, long periods of quiet would have allowed the galaxy to cool back into its present state of stillness. In simple terms, the dark heart at the center acts both as an anchor and as a slow engine, converting in falling matter into energy that keeps its environment gently stirred. The importance of this dark heart reaches outward to the whole cluster. By regulating how gas cools and how new stars form, the black hole helps set the character of the central galaxies. Old red populations and smooth light profiles tell a story of early growth, followed by long, steady maintenance. NGC 4889 stands as a clear example of this path. Its extreme black hole mass inferred from the motions of its stars may bend common scaling relations at the high end, but it does so in a way that fits naturally within the deep potential of the Coma Cluster. The galaxy and its dark core are not anomalies. They are natural outcomes of gravity acting in a rich, crowded environment over great stretches of time. Standing at this final descriptive horizon, the narrative does not need to imagine what happens inside the black hole. It is enough to trace how its presence shapes the space around it. From the rising velocity dispersion to the carved inner core from the heated intracluster gas, to the quiet extended halo of stars, each layer carries a gentle imprint of the central mass. The story of NGC 4889 and its supermassive black hole is therefore not a tale of threat, but of structure. It shows how a dark heart can stabilize rather than disturb holding a galaxy, together within a cluster that remains calm on human timescales. With this view in mind, the image of NGC 4889 settles into something clear and peaceful. A giant elliptical galaxy rests in the core of the Coma Cluster, its old stars shining steadily, its halo blending into the cluster light, and its central black hole sitting in deep silence. The dark heart cannot be seen, but its quiet pull organizes the motions of stars, the shape of the core, and the gentle balance of gas and gravity that surrounds it. The Coma Cluster lies far away, yet in this quiet moment it feels simple and ordered. NGC 4889 rests at its center, a smooth ellipse of light suspended in the cluster's deep gravitational well. Around it, the faint halo of stars blends into the intracluster glow, and beyond that the wider web of dark matter holds everything in gentle place. The central idea can stay very soft now. A single galaxy with a single dark heart sits within a calm, long-lived structure. Its stars have finished most of their changes. Its gas is thin and quiet. The great black hole at its core has grown heavy and settled, shaping orbits and heating gas in distant ages while remaining silent on human timescales. From the outer cluster, halo inward to the event horizon, each layer of this system follows clear rules. Stars move in stable paths. Hot gas drifts and glows. Gravity gathers matter, but does not rush it. The central mass deep inside NGC 4889 may be extreme, yet its effect is to hold the galaxy together, not to disturb it. In this view, the universe appears steady rather than wild. Large structures form, evolve, and slowly relax. NGC 4889 becomes a symbol of that slow settling. Its light is old and soft, its core is dark and firm. The cluster around it provides a broad, secure backdrop. Nothing in this picture demands quick change. Everything moves on scales so vast that for a long stretch of time it all seems almost still. With that image in mind, attention can drift away from details. The giant elliptical fades back into the distant sky. The Coma Cluster becomes one quiet node among many in the cosmic web. What remains close is only the feeling of a stable, layered universe gently organized around hidden centers of gravity that hold their surroundings in place.